In this video, we're going to cover mass spectrometry, looking at molecular mass and high-resolution mass spec, infrared spectroscopy, looking at how this works and how to identify different functional groups, then looking at the chemical tests for various functional groups, alcohols, aldehydes and ketones, carboxylic acids, alkenes, chloroalkanes, and acyl chlorides. You'll find it useful to have access to the A-Level Chemistry datasheet throughout this video. We'll be using the periodic table when looking at mass spec, and the infrared table when looking at the infrared topic. You'll have looked at how mass spectrometry works in detail in your first physical chemistry topic. Mass spectrometry can be used to find the MR, or the relative molecular mass, of a compound or molecule. This is given by the molecular ion peak on a spectrum. We can then use this to identify what a compound would be. So for example, this question says, the mass spectrum of a straight chain alkane contains a molecular ion peak with an MZ, or a mass to charge ratio, of 72. Identify the compound. So we know that the M to Z equals 72. Therefore, the molecular mass of the compound equals 72. We know that the alkane is a straight chain, so it's going to be some variation of CH3, CH2, CH2, etc. So the majority of the chain is going to be CH2 groups. And we know that CH2 groups have a relative mass of 14, 12 for the carbon and 2 for the hydrogens. Therefore, to calculate a rough estimate of the number of CH2 groups, we can divide the MR by 14. So we would do 72 divided by 14. And this would give us an answer of 5.14. It makes sense that the answer is slightly above a whole number, as we know we're going to have a CH3 on either end. So in this case, we could check to see whether the MR of the chain would have 5 carbons in it. So we'd need to work out the MR of an alkane with 5 carbons. So that would be C5H12. So that would be 5 lots of 12 for 5 lots of the carbon, plus 12 lots of 1 for 12 lots of the hydrogen, giving a final answer of 72, which is what we were told at the start of the question. So we've identified the compound as being C5H12. High-resolution mass spectroscopy machines can be used to measure the relative molecular mass to several decimal places. This can be used to distinguish between molecules which have the same whole number molecular mass. We're given these in the question, so you won't find these on your periodic table, but you can get the accurate molecular masses to 4 decimal places given in a question which requires you to use this. So for example, this question says, on a high-resolution mass spectrum, a compound has a molecular ion peak with MZ 98.0336. What is its molecular formula? And we're given 4 options. Each of these 4 options will have a whole number mass spec, or a molecular ion peak, of 98. So if you use your periodic table to work out the MR of each of these, they would all be 98. But we've got the precise masses here, so if we work out the precise molecular mass, only one of those will equal 98.0336. So we'll work out the precise MR of each of these 4, starting with A. You'll have to show your calculations clearly for each question, and it's a good idea to set it out by doing the number of the atom you've got times the MR of the atom each time. So A has a precise MR of 98.0842. We would then repeat the calculation process for B, giving us a precise MR of 98.0729. Do the calculation again for C, giving us 98.1092. And finally, do the calculation for D, giving us a precise MR of 98.0336. Therefore, the correct answer is D, C5H6O2. We're now going to learn about infrared spectroscopy. Infrared radiation consists of frequencies between 500 centimeters to the minus 1 and 4,000 centimeters to the minus 1. A beam of infrared radiation is passed through a sample, and a detector determines which frequencies of IR radiation have made it through the sample. So for example, we've got two bonds present here. We've got a CH bond and a C double bond O. IR radiation is absorbed by the covalent bonds in a molecule. Different types of bonds absorb different frequencies of infrared radiation. Therefore, the frequencies of IR radiation which have not been detected must have been absorbed by the bonds, and therefore we can look at what bonds must be present in the sample by which frequencies of infrared radiation have been absorbed. So for example, in this case, we know a C double bond O would have been present because our detector would have told us no IR radiation in this wavelength has made it through, which using our data sheet we know would correspond to a bond of a C double bond O. Likewise, no radiation in the 2850 to 3300 range would have been detected. Therefore, we know that bond must have been present in the molecule because it's absorbed that radiation rather than letting it pass through and go to the detector. Therefore, a CH bond was present. This table here is provided in your chemistry datasheet, and you'll use it during any work on IR spectroscopy. This will tell you what frequency of radiation corresponds to which bond. We'll have a look at what this looks like on the spectra in a moment. The region between 1550 and 1000 centimeters to the minus 1 is called the fingerprint region. It is unique to a particular compound. You can check the region of an unknown compound's IR spectrum against that of a known one, and if it matches, you know what the molecule is. It can also be used to determine the presence of impurities in a sample. They'll show up as extra peaks in the fingerprint region. This is what an IR spectra looks like. It shows you the percentage transmittance, so how much of this wavelength has made it through to the detector of each wavelength of light. We're going to look for where the peaks are in these spectra. A peak corresponds to a bond, because if there's a low percentage of transmittance, it means the majority of that infrared has been absorbed, therefore the bond which absorbs that infrared must be present. I'm now going to show you how we would identify each peak and each bond in the molecule. Remember, we're only going to look at things outside of the fingerprint region, so anything in the below the 1500 range will not be considered, so we don't look at the fingerprint region. So the first peak outside of this fingerprint region we're going to come to is this small peak here. This peak is in the 2850 to the 3300 range, so it falls within that range of the IR band. Therefore, comparing that range to our datasheet tells us that it's a CH bond. These ranges won't always be precisely what you will see on the diagram. So your range won't fully cover where the peak is. So for example, it won't precisely start at 2850 and it won't finish at exactly 3300. You've got to use your judgment to decide which range you think that peak falls in. This is the next peak we're going to look at. It falls within the 3230 to the 3550 range. So by checking on the datasheet for this range here, we can see that bonds that fall within this range are going to be the OH alcohol peak. So therefore, this bond represents an OH group. We'll do exactly the same on this spectra, so identifying the peaks beyond the fingerprint region. This is the first peak we're going to look at. This peak falls within the 1680 to the 1750 range. And checking on the datasheet shows us that this will be a carbon-oxygen double bond. We can't tell whether it's an aldehyde or a ketone. We'd have to do further chemical tests on the sample to identify them. We can just tell what type of bond it is. This is a very characteristic peak for a carbon-oxygen double bond. It's a long, thin peak. We'll now look at this group. And this would be a CH group. I've coloured this in blue rather than red because all the molecules we're going to look at have a CH peak. Normally you will not get marks for identifying a CH peak. We can assume if we're working on an organic molecule, CH will be present, so we generally don't identify that separately. We can just assume it's there and focus on the other functional groups instead. This is the first peak we're going to look at. It falls within the 1680 to the 1750 range. We've just looked at this on the previous example, so we know this is going to be a carbon-oxygen double bond. Again, it's that characteristic long, thin peak. This is the next one we're going to look at. This peak here is a characteristic OH acid peak. So even though the range is 2500 to 300, it does extend a bit beyond 3000. But you've got to learn that this peak is what an OH acid, so a carboxylic acid peak looks like. You can tell the difference between a carboxylic acid peak and an alcohol peak because they're both OH and they're both in a similar range, because the CH peak, which is around here, merges into the OH acid peak. So if it looks like one very, very big peak, then it's the OH acid because it's merged in with the CH peak, which is why it extends and distorts the peak a little bit. If you look at the previous example where we looked at an OH alcohol, the peak was very separate from the CH peak. So check back on example 1 if you want to see the difference between an OH acid and an OH alcohol, but this peak here you've got to recognise as being characteristic of an OH acid peak. Again, as discussed a moment ago, we wouldn't categorise the CH peak separately as we know it's going to be there, but I'm now just highlighted that it has merged with the OH acid peak. So if we're trying to identify what functional group will be present in this molecule, we've got a carbon-oxygen double bond, an OH acid bond, put these two together, and that would be a carboxylic acid. We'll start off identifying this peak first in this example. So this peak is in the 3300 to the 3500 range. So this would represent an NH bond. This isn't one which is commonly asked in exams, but I've included this to show you the difference between an NH bond and an OH one. The OH peaks are very broad, you typically get a very low transmittance, so the peaks are very close to the bottom, and an H bond will normally look like this. So it's just how you can avoid getting this mixed up with an OH alcohol or an OH acid peak. And we also have our CH peak as well. IR radiation is the cause of global warming. The sun emits UV radiation, which is absorbed by the Earth's surface and then re-emitted by the Earth's surface as infrared radiation. Greenhouse gases consist of carbon dioxide, water vapour, and methane. As we've just looked at, we know that bonds absorb infrared radiation. So, the greenhouse gases absorb the infrared radiation being emitted by the Earth's surface. Once they've absorbed it, they then re-emit that radiation back out again. Some of that travels down towards the Earth, heating it up. The more infrared radiation absorbed by a greenhouse gas, the better greenhouse gas that it is, i.e. the more insulating it is, because the more IR it can absorb and therefore release back towards the Earth, heating it up further. We're now going to look at the chemical tests for a variety of different functional groups. We'll start off by looking at an alcohol, which is the OH functional group. To test for an alcohol, we would add acidified potassium dichromate. If we have a primary alcohol or a secondary alcohol, it will oxidise it, and we will see a colour change from orange to green. Just remember, this will only test for primary or secondary alcohols, as tertiary alcohols can't be oxidised. So to test for aldehydes and ketones, which have the CHO functional group for aldehydes and the CO functional group for ketones, we can add Tollens reagent and heat, or we can add Phelan solution and heat. If we've used Tollens reagent, an aldehyde will produce a positive result, a silver mirror. A ketone will show no change. If we've used Phelan solution, an aldehyde will show the positive result, the blue solution go into a brick red precipitate. A ketone will show no change. And both of these are because aldehydes can be oxidised further to carboxylic acid, which is what is happening during this process. Ketones can't be oxidised, so there is no reaction. We'll now look at carboxylic acids, which have the COOH functional group. And to test for them, we would add sodium carbonate. And we would see bubbles fizzing, we'd see the carbon dioxide being released. This is because the sodium carbonate would react with the carboxylic acid to produce carbon dioxide gas. We'll now look at alkenes, which have the carbon-carbon double bond functional group. To test for those, we would add bromine water, and a positive result will be a colour change from orange to colourless. You also need to know how to test for chloroalkanes. So this is the CCl functional group. You would warm your chloroalkane with silver nitrate, and a positive result would be a white precipitate of silver chloride.